Good morning, children, and welcome back to our class 10 mathematics, real numbers. We already learned about rational numbers and real numbers. We have discussed types of number systems. We have discussed, and Euclid's division lemma we have discussed. Now it is time we discuss about the fundamental theorem of arithmetic. So, looking at the word, you might feel it's a very big thing, fundamental theorem of arithmetic. But if you go deep, it is nothing. We know all these things, but we are learning it as a theorem now. Until now we know that logic, but now we are going to formalize it as a theorem. Let's see what is this fundamental theorem of arithmetic. Now let us suppose if I ask you to write factors. Remember factors of say 36. Write all the factors of 36. When I ask you write factors of 36, so what we were doing it in the earlier classes, that is from 6th standard onwards, that is 36. Which and all tables it will come. Naturally, for every number, 1 is a factor. One table, every number comes, so it's a factor. And it itself is a factor. We know these two factors. For any number, 1 and itself will be a factor, so we know these factors. And other than these, we will be writing some more factors. Now, let's check number by number. 2 table? Yeah. 2 table, because it's an even number, it comes in 2 table. Very good. Now coming to next number, it is 3 table. 3 table, 3 ones are 3 twos are 3 12s are 36, so we know 3 is a factor. 4 table, 4 nines are 36. Very good. 5 table, to be in 5 table, the end must be the last digit, the ones place must be 0 or 5, but here we don't have 0 or 5, so it won't come in 5 table. Now let's come to 6. So 5, the chance is not there. Now coming to 6 table, yeah, 6 6 are 36. Now 7 table, 7 5 is 35, and next number is 7 6 is 42. We don't have 36 in 7 table. Now coming to 8 table. 8 table, 8 4 is 32 and 8 5 is 40, and there is no 36 in 8 table. Very good. And in 9 table, 9 4s are 36. Now that you have got 9 4s are 36, so automatically you need not check all other numbers. The next number will be the divisor of when you divide 36 with 3, whatever is the quotient you will be getting, that will be the next number. That is 3 table, 3 12s are 36, and 2 table, 2 18s are 36, and 1 table, 1 36 are 36. So this is how we used to write factors of a given number. So these are the factors. Now we are going to learn in factor writing. We know now we are going to divide the same 36 into factorization. What is a factorization? Factorization means dividing it in, writing it in form of factors. Let us write this as 6 6 are, or you can write 9 4s are. Now further we write this 9 as factors and 4 as factors. 9 we can write as 3 3s are, and 4 you can write as 2 2s are. Is there any other option? No. Now where we are ending this factorization process, where are we ending this factorization process? We are ending it when we get the prime numbers, that is the numbers which doesn't come in any other table than 1 and itself. So these numbers we used to call prime numbers, and this 36, if you observe carefully, can be written as 3 into 3 into 2 into 2. So 3 3s are 9, 3 3s are 9, 9 2s are 18, 18 2s are 36. So however you try, same 36 you try in another way. We have taken in earlier case 9 4s are, now we are taking for example 2 18s are. 2 18s are 36. Now let's divide this 18. 2 9s are. Let's divide this 9. 3 3s are. So here what we are getting, 36 is equal to 2 into 2 into 3 into 3. Now let's observe the previous page. Here we got 3 into 3 into 2 into 2. That is 3 square into 2 square. Now in this page we are getting it as 2 into 2 into 3 into 3. That is 2 square into 3 square. If you observe these two carefully, answer is finally same. 36 is either in first page we got 2 square into 3 square, and second page we got 3 square into 2 square. So what we are concluding here is exactly the fundamental theorem of arithmetic. Confused? Let's see. So what is the fundamental theorem of arithmetic saying? The conclusion is See, observe here in this page number 9 of your textbook, the prime factorization, exactly this part. Which part? The part that is highlighted, that is the prime factorization. The prime factorization of a number, the prime factorization of a number, of a natural number, is unique except for the order of its factors. That is, in the previous case we have learned that 36 when we have factorized 2 square into 3 square. So first time when we factorized, we got 3 square into 2 square. So the prime factorization here is unique. 2 comes 2 times and 3 comes 2 times, that's it. The order may differ. Here someone got 2 square into 3 square, someone got 3 square into 2 square. The order may change, but basically the prime factorization will remain the same. So this is the fundamental theorem of arithmetic. So write down this in your notebook. So now we are going to discuss, okay, we have theorem, we have made it a theorem. We know that it from so many years, but still we made it a theorem. We called it fundamental theorem of arithmetic. Now what are the uses? Applications means nothing but uses. What are the uses of this fundamental theorem of arithmetic? Here we are going to do, there are so many uses, but we are going to do 3 different kinds of sums. We are going to find out LCM using this fundamental theorem of arithmetic, and HCF. So LCM, HCF based sums we are going to do, and we are going to do divisibility tests. Something like divisibility based questions also we are going to do. So why wait, we will start them. Now let's learn how to find HCF and how to find LCM using this fundamental theorem of arithmetic and prime factorization. Using these methods, how we are going to do this? Let us see. 36 we already know, 2 into 2 into 3 into 3, and 24 you have to do. Let us do 2 table, 2 12s are 24, again 12, 2 6 are 12, again 6, 2 3s are 6. So this is how we have first for example we have to find out 36 and 24's LCM and HCF. So for HCF purpose, what we are doing, whatever is common, like 2 is common, so HCF is the common things we find out and we take out 2. Don't think that here there are two 2's are there, so we will take 1 2 only. Again, what is common in both the things? 2. Again, what is common? Here 2 is there, here 2 is there, here 3 is there. We cannot, that is not common. Whereas here it is common, 1 3 is there. So HCF is 2 into 2 into 3. So this is how we find HCF. Whatever is common we will write. Now how to find LCM? LCM we will take, like whatever is HCF parts we will leave. So other than HCF, what is there? For example, here this part and this part we have not taken common. Here this common we have taken, this common we have taken, and this we have taken common. So after taking these common things, whatever is left out we will take. 3 is left out and 2 is left out. So we will take this and we will write that as LCM and HCF. So HCF is 2 2s are 4 3s are 12, and LCM is 2 2s are 4 3s are 12 3s are 36 2s are 72. So this is how you are going to find HCF and LCM in the next exercise. But every time you need not take this way. There is a shortcut method also. Let us see what it is. This way also we can do, where we write the common factors. What are the factors? 2 is there and 3 is there. So we write them here, and for HCF we take the least power things, that is 2 out of 2 cube and 2 square, what is the least power? 2, so 2 square, and out of 3 and 3 square, what is the least power? 1, so 1. 2 square into 1, that is 4 3s are 12. This way also you can write. Similarly for LCM, instead of least power we take the highest power. So here for HCF we have taken the least powers. Now let's take for LCM purpose highest purpose. So what is the highest among 2 cube and 2 square? That is 2 cube. And what is highest among 3 and 3 square? That is 3 square. So 2 cube is 8, 3 square is 9, 8 9s are 72. Like this also you can find HCF and LCM using prime factorization. Now there is another interesting property in this HCF and LCM, that is, if you do for example, you are finding HCF and LCM of two numbers A and B. Now, if you multiply these two numbers, it is equal to product of HCF and LCM. Want to check this formula? Let us check with that our 36 and 24 example. 36 is 2 into 2 into 3 into 3, and 24 is 2 into 2 into 2 into 3. Now what we are doing in the name of HCF, when you multiply these two numbers, all numbers will come. That is 36 into 24 is nothing but 2 into 2 into 3 into 3 into 2 into 2 into 2 into 3. So we are multiplying all the numbers. Now from right side we are checking. HCF means whatever is common you are taking only once. 1, 2 is common, so you are taking this 2. And another 2 is common, so you are taking this 2 also. And 3 is common, so we are taking this 3 also. So that is how HCF is coming, 2 into 2 into 3. Now for LCM what we are doing? We are taking these common things, that is 2 is common, you are writing, and 3 is common, that also you are writing, and whatever is left out also you are writing, that is 3 into 2. Now so this is HCF and this is LCM. Now when you are multiplying these two things, let us see how many 2's are coming. 1, 2, 3, 4, 5 2's. So here also in this case 1, 2, 3, 4, 5 2's. Similarly 3's also 1, 2, 3 3's. So here also 1, 2, 3 3's. So this is how we write this formula. So two numbers HCF and LCM is A into B is equal to HCF into LCM. In our exercise they are going to ask these questions in this way, like they will, out of these two numbers they may give one number, they will give HCF and LCM, they'll ask you to find the value of, find the second number. In that case what we do? B is equal to HCF into LCM by the first number. Sometimes they will give you HCF, they will give you both the numbers, and they'll ask you to find out LCM. In such case what we do? LCM is equal to product of numbers by HCF. Similarly HCF is equal to product of numbers by LCM. This way we will be solving those sums. Now let us see the exercise number 1.2. So here the first number they are giving is that express each of the product as prime factors. So simply you will take the number and you will for example here if I take 140, you will divide it in whatever way you want. 2 into 70, 70 again 2 into 35, again 35 you can write 7 into 5. This way you will be writing all these things, and finally you will get the answer. 140 is equal to 2 into 2 into 5 into 7, that is 2 square into 5 into 7. So this is the prime factorization. The same way you will do for 156, 23825, 5005 and 7429. Now we are discussing about the second exercise, second Roman, that is find LCM and HCF of following pair of integers and verify LCM into HCF is equal to product of two numbers, that is A into B. This also you can do like we have done for 36 and 24, you can do. And in the third Roman they are asking find the LCM and HCF of following integers by applying the prime factorization method, that is same, but here there are three things, so three things you have to be little bit careful. Now let's solve one of the sums, that is 12, 15, 21. What is 12? 2 into 6. Again 6, 2 into 3. What is 15? 3 into 5. And what is 21? 21 is 3 into 7. So what is common we will be writing. What is a common thing? 3. There is only one 3. So that is HCF. And what is LCM is the number, other 3 we will take only one time and rest all we will take, that is 2 into 2 into 2 into 5 into 7 into 3. 2 into 2 into 5 into 7 into 3. That's it. This is how you are going to find. Here what is it, how is it different from second Roman is that here you are doing for 3 numbers. Now coming to the next question, that is HCF is given and both the numbers are given. They are asking you to find LCM. We have discussed this formula. HCF into LCM is equal to A into B. A is 306, B is 657 and HCF is 9. You have to find just the LCM. And coming to the next question is somewhat different. Here it is the another application of fundamental theorem of arithmetic. We told fundamental theorem of arithmetic applications when we were discussing, there were two things. First thing was HCF LCM, second thing was divisibility. Now we are discussing about this divisibility. Now check whether 6 power n is divisible by number can end with 0. whether 6 power n can end with 0 or not, they're asking. So we know that to end for any number to end with 0, we need to either have a 5 or 2 in its prime factorization. 5 or 2 when they are there, then only we will get 10. Otherwise there is no chance. Instead of, if there is no 5 no 2, how we will get 0? So there is no chance at all. So let us see, in expansion of 6 power n, 6 can be written as 2 into 3 and whole power n. So what is the prime factorization of this number? 2 power n into 3 power n. So in this prime factorization, we neither found 5, neither found 2 is there, but 5 is not there. So we write, since in its prime factorization 5 is not there, we can say it is not divisible. 6 power n is not divisible by 10, and it will never have 0 in its ones place. That is how we are going to answer that. And coming to the next question, again next question, right, explain why 7 into 11 into 13 plus 13 is a composite number, or they are asking show that they are composite numbers. Sometimes question will come show that, or sometimes they'll ask explain why. So here in this case you have to observe these are all divided into, and this is plus. So here there are two terms. First term is all connected with into, and then plus. This differentiation you must observe. Now out of these two terms, one term is common, one number is common, that is 13. You take that as common. What is left out? 7 into 11 and plus what is left out here? 13 has gone, so it is 13 into 1, so we have got 1. So 13 into something, that can be anything. 77 plus 1, 78. Even if you don't simplify, no problem. So we are writing it as product of two numbers. So it is a composite number. If you are not able to write this into prime factor of some other, like other than 1 and itself, if you don't find any other factor, then only it is a prime number. Otherwise it is a composite number. So you can write. Similarly, in the second, in that again we have another number, that is 7 into 5 into, see where the plus is, plus 5. So you can keep a bracket and you take that 5 as common, and 5 into something you are able to write it. So it is not a prime number, it is a composite number. And now that there is only one question left, that we will see. Now read the question. There is a circular path around a sports field, and Sonia takes 18 minutes to complete. So Sonia's speed is 18 minutes in one round, for one round, and same thing, Ravi takes 12 minutes. Ravi is a little bit faster, so he's having only 12 minutes to take this round. So Sonia and Ravi. So Sonia takes 18 minutes. So after 18 minutes, both are starting at same time. So after 18 minutes, she will reach this point again. And after that, 18 2s are 36. After second round, after 36 minutes, she will reach there. And 18 3s are 54. She will reach there. Similarly, Ravi, after 12 minutes, he will reach there, same point. But by the time he came near 12, she is taking 18 minutes, so they both will not meet. And second round, he will complete in 24 minutes. And third round, he will complete in 36 minutes. So when he is completing his third round, this Sonia is completing her second round. So what we can observe, exactly at 36th minute, both are at same point. So this is how we have to solve this. Since the numbers are small, we are able to write their tables and we are able to find this answer. Otherwise, what is the process? The process is simple. These numbers 18, 36, 54 are multiples of 18. And 12, 24, 36 are multiples of 12. Now this 36 is common multiple of this 18 and 12, and you will get again 72 like this. So what we have, simply they are asking us to find out least common multiple, LCM. You have to find out for 12 and 18. Now that we have discussed in prime factorization method, you can find out the LCM and you can write the answer at 36 minutes. Here in prime factorization, 2 6 are 12, again 6 2 3 are 18, 3 6 are 18, and 6 you can write 2 3 are. Now what is common? 2 is common and 3 is common, so we will write this common numbers only once, and other numbers we will write 2 into 3. So 2 2s are 4 2s are 8 3s are 24. Sorry, like here 1 2 is common and another number that is common is 3. So one is 2 common and another is 3 common. So 2 3, and other then left out are 2 into 3. So it is not 24, it is 36. So this is how you are going to solve this sum. So that is the end of exercise 2. Not only exercise, we have exemplar sums also. So in this model, first you do the exercise and tomorrow we'll be doing some exemplar sums. Thank you. Bye.